Hello, bonjour, kia ora. I'm Adrian, it's June 21, and this is AInVFX News. Today, we've got 4 practical techniques to explore. We'll start with MagCache, a new acceleration technique that makes video diffusion models 2 to 3 times faster. Then we'll dive into NAG that brings back negative prompting to distilled models. DLoRAL shows us how to upscale video with dual LoRAs in a single step. And we'll finish with something a little different, MIT's approach to art restoration using AI and polymer films. Allez, on y va. Let's talk about MagCache, a new acceleration technique for video diffusion models that came out last week. The researchers from Peking University and Huawei discovered something interesting about how diffusion models work internally, and they've turned that discovery into a practical speed-up technique. Video diffusion models are slow. The reason is simple. For production quality, these models typically run 30 to 50 denoising steps. With large models like 12.114b, every step requires massive computation. Previous acceleration methods like Tcache try to intelligently skip computation steps. Tcache analyzes 70 different test prompts and uses polynomial fitting to predict which steps can be safely skipped. In simpler terms, they gather data points from all these test runs, then fit a mathematical curve through them to create a prediction model. The paper shows this approach has a fundamental weakness. When your actual prompt differs significantly from the 70 calibration prompts, the predictions become more unreliable and results can vary widely. The MagCache researchers discovered a unified magnitude law. When they measured the residual output at each denoising step, they found the magnitude ratio between consecutive steps follow a universal pattern. It decreases slowly and smoothly for about 80% of the journey, then drops rapidly in the final steps. This pattern is remarkably consistent across different prompts and even different models. Instead of complex calibration, MagCache uses pre-calculated magnitude ratios embedded directly in the code. One pattern works for all prompts on that model. MagCache tracks accumulated error as it skips steps. Let me break this down. The accumulated ratio starts at 1 and gets multiplied by each step's magnitude ratio. This tells us how different the current output is from what we cached. The error is calculated as how far this accumulated ratio drifts from 1. 2 user parameters control the skipping. If the total error stays below your threshold parameter, and it hasn't exceeded your K parameter from consecutive skips, it reuses the cache residual. Otherwise, it computes that step properly and resets the counters. Most video models use CFG, or classifier-free guidance. This means they run the model twice per time step, once with your text prompt, once without it. They then combine this output using your CFG scale. A higher CFG scale, like 7, pushes the generation more strongly toward your prompt, while lower values, like 1, give more freedom to the model. MagCache needs to handle both these passes. In theory, it could track the magnitude ratios independently and skip the conditional or unconditional pass separately. But in the current ComfyUI implementations, both passes are linked. If the magnitude ratio says to skip, both skip together. If it says to compute, both compute together. This simplifies the implementation, but may not be optimal for all cases. Let's dive in ComfyUI to see this in action. Go into the manager, custom node manager, and search for MagCache. This is the official implementation. If you prefer, you can also use the one video wrapper from Kijai, which has been updated to support MagCache. Either way, make sure both of those node packs are up to date. There were quite a few bugs in the official implementation this week that I reported and got fixed, so you definitely want the last version. Let's start with Kijai's implementation. Go into the workflow, browse template, and load under ComfyUI one video wrapper the text-to video example workflow. Gonna rename that to MagCache. I'm gonna tweak a few settings to make sure everything runs smoothly on my hardware. So I'm gonna enable touch compile. I'm gonna set it to FP16 fast and sage attention. I'm also gonna reduce the block to swap to 15. That should keep my VRAM usage under control. I'm making sure all the paths are set properly. I'm going to set the seed to 42 because it is the answer to the ultimate question of life, the universe, and everything. Steps to 25 should be fine. I remove enhance the video to keep things simple. I don't need Tcache for now. And I'm going to clean up some nodes that are not needed for that example. Okay, let's start with our ground truth. I'm going to rename that as wrapper ref, and let's run that generation. I'll speed up the video and we'll see you once this is done. That was about 920 seconds, 25 steps. And we have a bird landing on the panda. Okay, let's try with MagCache now. Duplicating that workflow, let's rename the output to wrapper cache. I'm going to load one video MagCache node, and I'm going to connect it in the cache args. In terms of the settings, we're going to leave the threshold to 0.02, which is a good trade-off between speed and quality. Going to increase the key value to 6, which is going to tell MagCache it can skip up to 6 consecutive steps. And I'm going to set the start step to 5 to ensure the process doesn't start before step 5. We don't want to affect early steps as it's going to break the generation too much. A value of 5 will also ensure a better consistency between our ground truth and our MagCache version. I'm going to leave the end step to -1 so MagCache can keep working until the very last step. We also have the cache device to offload on the CPU if we want to. Let's disable the previous output and run the generation. 424 seconds, that's about 2x faster. And if you check in the shell, it's telling you that it skipped 14 steps. And if you compare the output quality, it is different. Like you see, the feathers are different because there are less steps. However, there is no big visual quality loss between those two versions. Let's bypass that one and let's compare now with Tcache. Renaming to Tcache. Instead of using the MagCache, I'm going to use a one video Tcache. Connect the cache args into cache args. In terms of settings, we're going to set threshold to 0.7 and start step to 5. That should give us similar results of what MagCache generated. Let's run the generation and we'll talk about it in a minute. The generation is done. That was 125 seconds, which is just 1 second over what we've done earlier with MagCache. That's roughly the same time. And we skipped 14 steps again. However, if you compare the steps, here we have 6, 7, 9, 10, 12. And earlier with MagCache, we had 6, 7, 8, 9, 11. So the steps are different because the logic between Tcache and MagCache are different. If you look at the visual quality between the two, you'll see it's fairly similar. However, it's a bit more burnt out in the face of the pandas and some of the feathers of the bird. Like we tend to have slightly lesser quality in the Tcache version. Okay, let's move to the native implementation. If you're working with native workflow, if we go into the template manager under ComfyUI MagCache, we should have a 2.1 text-to-video example. Let's grab that one. Gonna tweak a few settings to be consistent with what we had before. So let's keep the same prompt. For now, I'm going to remove the MagCache to have our ground truth version. Set the shift to 5, seed to 42, steps to 25, and ensure our model paths are set properly. I'm going to rename that to native ref and set the length to 81 now. Okay, let's run the generation. Because I do not have all the same optimization from the one video wrapper, I don't have torch compile, don't have P16 fast. It's going to be much slower. So I'll speed up the video and I will see you in a few minutes. The generation took just over 1300 seconds. So now we're going to bypass that one and compare it with the MagCache version. If I duplicate that workflow, rename it to MagCache. And we're going to be adding two nodes here. The MagCache and the compile model. MagCache is going to apply MagCaching, and compile model is going to apply torch compile, similar to the compile settings that we have with the one video wrapper. In terms of the settings to use, here we need to specify the model type. So in our case, we're working with text to video at 14B. Then we're going to use the same threshold we used earlier, so 2, and the retention ratio is a percentage. So 20% of our steps, so 20% of 25 steps, that means 5 steps. In that example, the MagCache process is only going to start from step number 5. If you don't want to set a percentage, you can set fixed step with a start step and end step value, similar to what we've done with the implementation in the one video wrapper. If you set both values, the model is going to look at the biggest numbers and only start processing from that number. In that specific example, if I set start step to 5 and retention ratio to 20%, it's going to give me the exact same result at leaving this one as default, or reducing that one and setting that one to 5. Okay, so just use either the percentage or the fixed step. You don't need to use both. Let's set the K value to 6 to be consistent of what we had before. And for the compile, I don't need to change any other settings. It's going to compile the graph the first time it runs. So it's going to be slower the first generation, but then it should be faster on any consecutive generations. Let's run that one and I will see you in a few minutes. So generation took about 1050 seconds, which is about 300 seconds faster than the previous one. Obviously, it's not as fast as a one video wrapper because I don't have all the optimization, but it's still better than nothing. If you were to rerun that graph one more time, because the compile is done now, it should still be a bit faster. In terms of quality difference, we are quite close. There isn't too much quality loss, so you could push those numbers even further if you wanted to. One difference worth noting is that the official implementation doesn't output in the shell the number of steps that were skipped. However, if you paid attention to the progress bar during the generation, you would have seen it jumped and skipped some steps. So it definitely happened, and the difference of execution time definitely confirms this. MagCache has some limitations. You need to work at high steps, above 20, to see real benefits. This is why if you're already using distilled LoRAs like CausVid or self-forcing, you won't get any value from MagCache. They've already reduced generations to 4 or 8 steps. There is nothing left to skip. Pushing parameters too aggressively causes quality loss. If you see artifacts, color shifts, or loss of detail, reduce the threshold and potentially the K value. The default parameter is optimized for speed, not quality. Some models like Chroma need custom calibration for different step counts. There is a MagCache calibration node for these special cases, but most users won't need it. Based on your settings, you can expect speed up of 2 to 3x with MagCache, similar to Tcache. However, the quality output should be better and more consistent. MagCache achieves this through its pre-calculated magnitude ratios and simple error tracking without requiring complex calibration or prompt-specific tuning. Whether you choose the official node or QGIS integration, you're getting real acceleration. The code and research are available under Apache 2 license. Give it a try and share your results in the comments. Now, we just saw how MagCache accelerates video generation by intelligently skipping steps. But what if, instead of skipping steps, you use models that are already distilled down to just 4 or 8 steps? When you use CausVid or self-forcing with 1.1, you get incredibly fast generations, but there is a major trade-off. Let me show you NAG, Normalized Attention Guidance, which solves this problem. Remember how we just explained that CFG runs the models twice per step, once with your prompt, once without. Well, here's the problem with distilled approaches like self-forcing. In a 50-step model, these two branches evolve gradually, like trains on parallel tracks, but compress that journey into just 4 steps and they rocket apart. By step 4, one branch is painting our panda on the bamboo stem, the other might be generating a completely different panda in a different setting. So what do people do? They set CFG to 1. This means the model only runs once with your positive prompt. No second unconditional pass, no blending, no artifacts. Your positive prompt still works, but you've lost the push-pull mechanism that makes negative prompts possible. Even when you try higher CFG values with these distilled models, you get severe artifacts. The positive and negative branches have diverged so dramatically that blending them creates visual inconsistencies. This is a fundamental trade-off of distillation. You can go as low as 4 steps, but you lose the fine control that makes video diffusion so powerful. Until now. NAG takes a completely different approach. Instead of trying to fix CFG for few steps models, it operates in a completely different space, the attention space. Here's what makes attention different from standard CFG. CFG blends the conditional and unconditional branches at every denoising step, step 1, step 2, and so on. But it's blending the noise predictions in latent space, the actual outputs at each step. NAG operates deeper inside the model architecture. While CFG waits for each step's output and then blends, NAG intervenes during the attention computation itself. This is like the difference between mixing 2 recordings versus adjusting the instruments while they're playing. The breakthrough discovery is that attention patterns remain remarkably stable even in distilled models. The attention mechanisms still know this region is a red bird and this area is a background with high consistency. It's this internal feature relationship that stay coherent even when the outputs being blended by CFG have diverged too far. Here is how NAG works under the hood. First, it computes what we call positive features, Z+, and negative features, Z-. Think of this as attention signatures. Z+ captures how your positive prompt influences attention, a bird. Z- captures how your negative prompt would influence attention, a red bird. Next come extrapolation. NAG calculates the difference between Z- to Z+, essentially finding the path away from what you don't want toward what you do want. It's like GPS navigation in attention space. Here is a crucial part, L1 normalization. This is a mathematical safety limit. Without it, the adjustment could become extreme and create artifacts. Think of it like a speed limiter on a car. You can steer away from unwanted features, but not so aggressively that you're gonna crash. Finally, alpha blending mixes the NAG adjusted features with the original attention. This gives you fine control over how strong the effect is. All of this happens in a single forward pass. No doubling of computation like CFG. The attention modification flows through the rest of the model, influencing the final output. Let's dive into ComfyUI to see this in action. If you've been following along with the previous demonstration, you already have the one video wrapper. If you don't, go into the manager, custom node manager, and make sure you have the latest version of the one video wrapper from Kijai. We're going to be reusing the same workflow as before. Go under workflow, browse templates, under ComfyUI one video wrapper, and grab the one video text to video example 02. Let's remove what we don't need. I'm also going to remove Tcache because we're going to be using a distilled model for that demo. Let me save the scene as NAG. I'm going to make sure I have all the right path for the model. Based on your own hardware, feel free to tweak the model settings. In my case, I'm going to turn on torch compile, FP16 fast, sage attention, and I'm going to set the block swap to 15 to ensure my VRAM usage remain under control. We're going to be working with the self-forcing LoRA. So using the one video LoRA select, grab the self-forcing LoRA and connect it into your model. If you don't have it, you can find the link to download it in the description. Because of the distilled LoRA, we need to make sure we work at low steps. We can use 4 and a CFG of 1. I'm going to disable tiling because I don't need it for that case. And I'm going to set the output to self-forcing ref. Let's run that version so we have a ground truth. Not bad for a 2-minute generation. Now let's bypass this one. Let's duplicate the workflow so we can experiment with energy. Let me rename the output to energy. And we're going to be using an apply energy node. The text embeds goes into the text embeds of the sampler. And for the input, we're going to use our original text embeds here. And then we're going to create another one video text encode single, where we set the T5 and the T5 and the text embeds into the energy text embeds. Here, we're going to set our negative prompt. So in this case, because I have a reddish bird, I can try writing red bird and see what the model is going to come up with. While we do that, let's look at the settings of the apply energy node. Energy scale, use strength control. For videos, the papers recommend 9 to 11. This determines how strongly we push away from negative features. Energy tau, the default is 2.5. This is a normalization temperature. Remember that L1 normalization safety limit? This parameter controls how strict it is. Energy alpha, the default is 0.25. The blending factor, we're mixing 25% energy adjusted attention with 75% original attention. And we've replaced our reddish bird with a blue bird. Just to confirm that this is working and the negative prompt from the original embeddings are not working, can bypass that output, duplicate the workflow again, can I rename it to ref negative. And if I now put the red bird into the negative prompt of the original embeddings, see what we get. And we're back to our red bird. So at the moment, this negative prompt is not being used. If you want to try, you could duplicate that workflow and experiment with higher CFG value. So if we set CFG of 7, let's rename the output to CFG and run that version. Now, see those artifacts? That's CFG failing at 4 step. That's why we said, if you're going to use distilled models, you need to use CFG of 1. Okay, and if you want your negative prompt to work, the only way to do it at this stage is using energy. One thing to remember, energy isn't limited to distilled model. It works equally well on standard 25 or 50 step generations. The difference is that with distilled models, it's often your only option for negative prompting. With standard models, you have a choice between CFG alone, energy alone, or both together. In that example, if you didn't use the LoRA and rerun that workflow, you could use a high CFG value and it would take into account your positive prompt, negative prompt, and energy embeddings. Let's talk about limitations. First, model understanding. Energy can't make the model generate concept it doesn't know. If the base model can't draw something, energy can't magically enable it. Second, parameter sensitivity. While the defaults work well, some prompts will need fine-tuning, so don't hesitate to play with the parameters on the apply energy node. Third, the research paper mentions energy adds 12% computational overhead to the attention layers, but in my tests, the impact on total generation time was minimal. So now you have a complete toolkit. MagCache for accelerating standard models by intelligently skipping steps, energy for adding negative prompt control whether you're using 4-step models or standard 50-step ones. Together, they help you optimize your workflow based on your specific needs. For those using self-forcing or CausVid, energy finally gives you back the negative prompt control you sacrificed for speed. The implementation is under MIT license, so don't hesitate to give it a go and share your results in the comments. Next up, DLoRAL, which stands for Dual LoRa Learning, a new approach to video upscaling released this week by Hong Kong Polytechnic University and Open Research. They've created a stable diffusion-based one-step diffusion model that achieves realistic frame details and temporal consistency simultaneously. Let's see how it works. Video upscaling faces a fundamental conflict. You want sharp, detailed frames, but you also need smooth motion between frames, what's called temporal consistency. Current AI methods struggle with this balance. Think of it like two trains on parallel tracks. The left train represents detail enhancement, making each frame crisp. The right train represents temporal consistency, keeping motion smooth. Previous methods connect these goals rigidly. When one pulls in its direction, it forces the other off track. Add details, you get flickering. Maintain consistency, you get blur. DLoRAL separates this task into two specialized modules called LoRAs, low-rank adaptation modules that efficiently modify pre-trained models. The consistency LoRA, CLoRA, handles temporal coherence. The detail LoRA, DLoRA, manages spatial enhancement. Each can optimize its task without compromising the other. They also introduce cross-frame retrieval, CFR. Instead of processing frames in isolation, it looks at neighboring frames for context. If this keyway is blurry in frame 2, but clear in frames 1 and 3, CFR uses that information to guide enhancement. It's leveraging the temporal consistency already present in the low-quality video. To train the LoRAs, they alternate between two stages. First, only CLoRA and CFR learn, focusing on temporal stability. Then, CLoRA freezes and DLoRAL learns to add details while respecting the established temporal structure. This cycle repeats throughout training to create the final model we'll use. DLoRAL builds on Stable Diffusion 2.1. The VAE, or Variational Autoencoder, compresses video frames to a latent space that's 8 times smaller in each dimension. So 512 by 512 image becomes 64 by 64 in latent space. The dual LoRa modules are then injected into the diffusion unit, which is a neural network that actually performs the enhancement in latent space. The VAE decoder then reconstructs the enhanced frames back to full resolution. Like adding specialized engines to an existing spacecraft without rebuilding the whole ship, the base remains Stable Diffusion, proven for image enhancement, now adapted for video. While methods like Upscale video need 30 steps, MGLD needs 50, and STAR needs 15 denoising steps, DLoRAL maps directly from low to high quality in just one step. This is the key to its speed improvement. On standard benchmark, like Video LQ, DLoRAL achieves top perceptual quality score across multiple metrics. Temporal consistency, measured by warping error, matches or exceeds existing methods. The standout achievement is speed. It's about 10 times faster than Upscale video, MGLD, and STAR. On an A100 GPU, processing 50 frames at 512 by 512 resolution takes about 5 minutes. The researchers acknowledge two main limitations. Since DLoRAL inherits the 8x downsampling VAE from Stable Diffusion, it struggles with very fine details, particularly small text. This heavy compression can also occasionally affect temporal coherence in complex scenes. They suggest a video-specific VAE could address these issues, but that would require retraining the entire system. For now, it's a trade-off they've made to leverage Stable Diffusion's proven capabilities. DLoRAL demonstrates that fast, high-quality video upscaling is achievable by decoupling competing objectives into specialized modules. Instead of forcing detail and consistency together, they let each optimize independently during training, then merge them for efficient single-step inference. The research paper is available, and the code should be released soon under MIT license. Watch this space. For our final story today, we're looking at a different kind of AI application, one that doesn't create new images but helps preserve existing ones. This comes from MIT, where a mechanical engineering graduate student named Alex Kashkine has developed a new approach to art restoration. Here's the reality facing museums worldwide. Countless paintings suffer from age damage, cracks, faded areas, missing paint. 70% of paintings in institutional collections are locked away from public view, many because they are too damaged to display and too expensive to restore. Traditional conservators work by hand, identifying damaged area called losses, then mixing exact color matches to fill each tiny spot individually. A single painting can have thousands of these damaged regions. Kashkine's new approach combines existing AI image analysis with a physical application method. The system first scans the damaged painting, then uses AI algorithm to create a digital version of what the painting likely looked like originally. But here's a key innovation. The digital restoration gets printed onto very thin polymer films, creating what it calls a physically applied digital restoration mask. Think of it as a transparent overlay that fills in all the damaged areas at once. Let me break down how this actually works. After cleaning the painting to remove past restoration attempts, the system scans it and identifies all damaged regions. For the 15th century oil painting Kashkan used in his demonstration, this meant 5,612 separate areas needing repair. The restoration requires two printed layers. First, a white backing layer, then a color layer on top. This two-layer approach is necessary because standard printers blend pigments together, which darkens colors. To achieve the full color spectrum needed, you need that white backing, just like how your printer needs white paper. These layers are printed on polymer films and carefully aligned on the painting, then adhered with conservation-grade varnish. The software Kashkan developed creates a precise map showing which colors go where, using 57 and 314 different colors for this particular restoration. Let's hear from Kashkan himself from a video published by Nature about the moment the mask was applied and what surprised him most about the process.
And once the mask was applied, the painting was visually restored. It was a lot quicker than doing so manually. That was really fun and also unexpected because usually when I restore paintings, I allocate months for doing so.
You can see in his demonstration how the painting transforms once the mask is applied, with all these damaged maps filled simultaneously rather than one by one. In this example, the infill process took 3.5 hours, an estimated 66 times faster than conventional in-painting, according to the paper published in Nature. Now, this isn't a universal solution. The method only works on varnished paintings that are smooth enough for the polymer sheet to lie flat. It can't handle three-dimensional textures or paintings with significant surface irregularities. There are also ethical considerations about whether having a film covering a painting is acceptable for high-value artworks. The technique is designed to be completely reversible. The mask can be removed using standard conservation solvents without leaving any trace. Kashkan tested the durability and found the mask could reasonably survive for a century if kept in appropriate lighting conditions. But as a professor from the University of Oslo commented, this approach is likely most applicable to paintings of relatively low value that would otherwise remain in storage, rather than famous masterpieces. What's interesting here is how this technology could democratize art conservation. Smaller museums without huge restoration budgets could finally display damaged works. The digital documentation means future conservators will know exactly what was done. It's not about replacing human expertise. Conservators still guide the entire process. It's about making restoration accessible at a scale that was previously impossible. Sometimes, the best use of AI isn't creating something new. It's helping us preserve what we already have. And that's a wrap for today. All the links are in the description below. If you learned something new, please like and subscribe. If you're experimenting with MagCache, NAG, or any of the techniques that we discussed today, drop a comment. I would love to hear about your experience. I will see you next week for another episode of AInVFX News. Thank you for watching.